Okay, so now I'm going to review the PDT and the EPANET supply together and show how to make them both accurate and match each other. So the first thing to look at is the elevations. In EPANET, your first elevation is the water level in the sump, that's 1328. And your final elevation is the water level of the tank or the top of the tank, 1423.1. That should be the same as the PDT. Now, I believe you used the survey elevations in EPANET, so we should use the survey elevations here in the PDT. 1328, 1423.1. The next thing is the pipelines. The pipelines should match EPANET. So, and you want to model all of your pipelines that you can. We only have 6 rows. I wish we had more. So we want to use these 6 rows the best we can to model the whole pipeline. And so we start with this GI pipe coming out of the sump and going and connecting to the HDP in the ground. There's 2 of those pipes. We can model that as one. There's a 1.5 meter GI pipe and a 7 meter GI pipe, and they both have 80 millimeter diameter, so we can model them as one. GI pipe at sump. Give it a good short description that identifies the pipe. It's 8.5 meters in length. It's 80 millimeters diameter. It's 120 roughness. And we had a total loss coefficient in those 2 pipes of 6. Next thing we want to model is the water meter itself. A water meter is about 0.5 meters in length. We chose a 2-inch water meter, 50 millimeter diameter, a roughness of 120 because it's metal, and a miter loss coefficient of 10. And when we run our model, you should check the head loss in the PDT and in the EPANET model and make sure it's similar. The next thing is we need to model the pipe main. Now we have 3 different pipe classes in our pipe main. We have a PN10, a PN12, and PN16. So we need to model those separately because they have a separate internal diameter. Let's start with a PN16, the first pipe we come to. I'll call it main 1. There's 2 pipes here in EPANET that are PN16, and the total length is 400, and the diameter is 73.6. So 400 meters of PN16 pipe, 73.6, roughness 135, and 0 loss coefficient. The next, I'll call it main 2. The length of, this is the PN12, the length in EPANET is 300. The diameter, let's check. So length 300, diameter of 76.4, roughness 135, 0 loss coefficient. And then the next is main 3. This is all the PN10 pipe. And that's 1,504. .2 inner diameter, 135, and 0 loss coefficient. And again, the reason these had to be entered as separate pipes is because they have a different diameter. So there's only 1 blank left. And we basically need to model all this piping in the treatment and going to the tank. So our treatment piping is 3-inch PVC. We have 2 pieces of 3-inch PVC. And then we have 3-inch GI. And unfortunately, those are different. So the best way to would be to model them as 2 separate pipes. We can't do that, but they're very close in diameter. So we can just model this all as 1 long pipe, 4.5 3, and 3. That's a total of 10.5 meters. Treatment, I'll say piping at treatment and 10.5 meters. We'll give it 79.2. I'll use 135 as the roughness, and then let's look at the total loss coefficient. 6, 0, and there should be a loss coefficient here. I should have added some loss coefficient to this pipe because there will be elbows and then an exit loss when it goes in the tank. So I'll put a loss coefficient of 4. So that's a total loss coefficient of 10. I'm going to add a little bit more because we had to use a roughness of 135 instead of 120. But you can see it's going to have very minimal impact on the total. So this is accurate enough. Okay, now we need to model the treatment losses, the actual treatment losses in the chlorinator. So erosion chlorinator, 3 units in parallel. And if you remember from the last video, we had about 54% of the flow going through the bypass. 50 to 60% is good. And then we don't have any other losses to model because we have accurately modeled everything in the system. If you feel the need to be conservative and to add 1 or 2 meters of head loss here, that's fine. But if you have modeled everything accurately, you shouldn't need to do that because things like this 135 roughness coefficient, that's conservative. So I would use 0 here if you've modeled everything else. And then, so we've made EPANET and the PDT match. So that's another reason to put 0 here, is the EPANET doesn't have any kind of blank for you to add 1 meter of head loss. So it's making it match the EPANET by putting 0 in the PDT. And now you can check and see if your two models match. Let's run this. Click on the pump to check the flow and head loss. 225 with 123 meters of head loss. 225.4. That's a flow rate of 13.5 meters cubed per hour. So I'm actually going to enter 13.5 here in the design flow rate so I can use the same flow rate to check and see if I have the same head loss. Head loss here is 122.9. In EPANET, it was 123.2. That is only off by 0.3 meters. That is very close, and that is a confirmation that your model is accurate, both EPANET and the PDT. So now if you want the design flow to stay at 13, you can change it back to 13, but because now you've already checked and you've seen that it's the same EPANET and the PDT. So these are the changes that I would make to your PDT to make them accurately reflect what you're planning to install on the ground. And another thing I would do is make sure the KMZ matches the PDT and the EPANET.